Good morning everyone and welcome to my YouTube channel. So for today we are looking at non-light microscopy. So under this one we are going to be looking at the atomic force microscopy. So atomic force microscopy and what we call the scanning tunneling microscopy. So what the scanning tunneling or the atomic force microscopy is made up of, it looks like this. So we have this part which we call the silicon holder. So the silicon holder is also known as the cantilever. So this is our cantilever. Then we also have the stylus here. Then we have our diamond tip. I've used different colors to make sure that at least you know the different parts. So we have the diamond tip. So the mechanism of how this operates, it's we know to say already at the surface of the diamond there are some electrons that are there. So now what happens if you bring in a surface, and we know the way a surface, let's say this is a surface, it will also have electrons on its tip. So when you bring in this atomic force microscopy, what begins to happen is that there shall be repulsion, because there are electrons at the surface and electrons on the surface of the specimen. So when you bring this closer, they begin to repel each other, they begin to push each other. So this means that, because we know to say one electron and another electron, they tend to repel each other. In other words, they more like push each other apart. Now instead of this whole thing going up, what begins to happen is that the cantilever, which is made of silicon, is flexible. You can just call it the silicon holder. Is flexible to such an extent that it bends. Instead of moving up, it bends like that. It might look like a structure that looks like this, thereby allowing the tip to sometimes not touch the surface. So there are two types of more like the atomic force microscopy. There is contact and non-contact. Sometimes there is under the non-contact we also have the tapping, but for the contact you can use it for dead organisms, because putting contact against the specimen may damage it. So the contact is mostly used for dead organisms, but if you want to preserve the undead organism, you need to use the non-contact approach, which we are going to discuss. So now the way it is, let's say for example, so let's say we have the specimen, we have the electron microscopy there. So let's imagine this is a specimen, it has got electrons on its surface. So what begins to happen is that as the electron force microscopy is moving, it will be moving like this. So it will be moving like that, going to the surface. So it is going up due to the fact that there is some repulsion between some electrons. So this is why it is moving up like that. It wants to more like stay into contact with a specimen, but due to the electrons that are on the surface and the electrons on the specimen, there is repulsion. So you can see that at all points it is more like trying to move like that. So it will continue to move like that. So now just ignore this part, it's only that it's a diagram, ignore it. Yeah, it's not in contact with that. So it is moving like that. So at all points it is tracing more like the specimen like that. So now this is very cardinal for us to understand. Now it's not necessarily that the cantilever, which is the silicon holder, is just fixed like that. Let's say if it was like this at one point, but as it moves here, it begins to bend like that, so that it does not stay into contact with the thing. So even here it is more like it should be bent, so that we have something like that. So this is how the electron microscopy works. Now it is this bending that will cause the light to change the position at which it will strike, which I will further illustrate as we move on. So this is the way it is. So we have the screen. So now as we look at the screen like that, you will realize to say, firstly we have the screen. Now we have this one we are going to call it a laser. So the laser hits our silicon, our stylus like that, then it bounces off to give us an image on the screen. So this is how it operates. When it strikes here, it will continue to strike. Let's say it strikes there, it strikes there, it strikes there, with relation to how the specimen is. So on the screen you can be able to trace something like that, and that forms your specimen. Let's illustrate this. So what we are going to do is we are going to memorize. So now, as the specimen is here, let's imagine, so it is used to measure the topography of the specimen. So as we can see, as the specimen is here, the laser is here. So now let's see what happens as our atomic force microscopy begins to move to our right. So we are going to find that it will be something like this. So it will move like that. So it is here now. We can just memorize the points. When we move like that, it has gone up there to match the specimen. So you will find that the laser is also matching where the specimen, how the specimen shape is. So if we move again, it will go up like that. Just imagine it's not touching the specimen. Then when it moves like that, it is on top. Then we move on like that, we can move on. So as you can see, the laser is tracing the specimen. So we are just going to draw everything there. So you are going to find that whatever we have there, it will be as a result of this. So we have something like this, then it begins to move down again. So now, as you can see, at all points, the laser will begin to be traced to come up with an image. So now if we are to look at the points at which the laser was, first it was here, it went somewhere here, it went somewhere here, it went up like that, went up like that, it went up, down like that, down like that. So you will realize to say the shape that is formed on the screen is actually the shape of the specimen. So this is something that you can realize, because this was where the laser was striking like that. So you will find that the shape of the specimen is like this. Even the shape of the image formed is like that. So this is how it works. So I told you that the cantilever, so let's say when it was here, it was like that. When it comes here, it has to bend like that. Now this bending causes the light ray to strike at another point. If it was here, let's say it was striking somewhere here, it changes where it's striking as a result of the bending of the cantilever, which causes the laser to more like be deflected to another point. So that is how the atomic force microscopy works. So do not forget that images that are formed are number one, 3D. The other thing is that you can use this to view cells, membranes, and proteins, even small structures such as our DNA. So you can be able to view that. Let's look at our scanning tunneling microscopy. So before that, as you can see, here we have the cantilever deflection, which is this thing, how it is deflecting, how it is changing shape. The change of shape can be like that. Sometimes it could be straight like that, depending on the bending and all that. Then here we have the topography. Topography is how the shape of whatever you are measuring is. So with this deflection, it will cause the light to hit at a different point like that. So let's look at our scanning tunneling microscopy. So this is our scanning tunneling microscopy. So we have the voltage there. We have it is connected to this one, which has a tip. So the tip is made mostly of an ultrafine of tungsten. So it is made of an ultrafine of tungsten. Then at the tip there are a lot of electrons. We call it a cloud of electrons, which can move from here to this. That's why it is called a tunnel. So we know that under normal circumstances, electrons tends to move from one object to another if they are in contact. But here they are not in contact. So they tunnel through. What we simply mean is that they jump from the tip to the to the specimen like that. Now, how does this work? Let's look at it in details before we can establish something. So now, let's say now this is a circuit, meaning to say there is a wire connected here. There was also a wire connected here. Now let's say that this tip is kept at a negative potential, meaning to say it has got a lot of electrons. So now if you look at this, the way it is, we want electrons to jump. They are not in contact, so we need an electron to jump. Now let's say that this is kept at a positive potential. So what begins to happen is that electrons will be able to jump from this point to this point. Now, since there is close interaction between the specimen and this tip, let's say here, just assuming, let's just say that 2,000 electrons flow. There is a possibility of 2,000 electrons flowing. It won't be the same as when the specimen is somewhere, when the tip is somewhere here. So remember, the distance is the same, like the vertical distance is the same. Now, you will find that the surface here is very far as compared to where the tip is. So let's say here, the number of electrons that on the flow are about just 200. So now, the number of electrons that flow will also determine the current. So now, let's say our voltage here reads. If it is here, since there are a lot of electrons that are flowing there, you will find that, let's say the voltage will be very high. It will be at this point. When we move to this point, the number of electrons that flow begin to be reduced. So as a result, there will be a drop in the voltage. So here, drop in the voltage. When we come here again, the voltage will rise like that. So since the voltage will rise, it will be somewhere here because the voltage has risen, because the number of electrons, let's say, comes back to 2,000 number. So the voltage will rise like that. So this rise in voltage will now be able to determine how is the specimen. Remember, there is no contact there. So it is more like the voltage that will enable us, the current voltage, it will be able to enable us to see how the specimen is. So that is how the scanning electron microscopy works. So let's look at another diagram. So this is our illustration. So as the electrons flow like that, there will be the electrons, let's say at this point 22,000 electrons flow, the voltage will be high. So as we move, since the distance is increasing, the distance from the tip to the surface of the specimen is very high, there will be a voltage drop to that point. So as we continue like that, you will find that the voltage begins to rise since the tip and the surface have got a close relationship. So the voltage begins to rise. At this point, the voltage becomes high. At this point, the voltage becomes at its highest. Then we can continue like that. So as it moves, the shape is created in such a manner. So here we can continue doing another waveform and all that. So that is how it operates. So just as we have seen, when we have more distance, low tunneling current, meaning to say when there is a greater distance between the tip and the specimen, then we are going to have a situation whereby we are going to have less tunneling current, as a result low voltage, which is more like the lower part of the graph. So now you are able to determine the shape of the specimen with respect to the voltage that is output. So this is a type of image that is formed. As we can see, it is a 3D image showing relief-like structures like that. So it is very, very important for you to view the specimen. How is the surface of the specimen? So it uses that way. So let's look at so the tip is made of ultra fine tungsten. That is very, very important for your description of the exam. So we know that more distance, that means low tunneling. A short distance, if it is here, it means to say more tunneling current. As a result, more voltage to be displayed on the screen. So that is how the atomic force microscopy and the scanning tunneling microscopy works. If you enjoyed the video, kindly like, subscribe and share for more. See you in the next tutorial.